inviting me here to give a talk. And well, most of you know that I spent 2 years in Barcelona, and I have wonderful memories. And it's good to be back and to speak. Well, let me see. It doesn't move. Sorry. So this is the contents of my talk, and this joint works with 2 of my students. And before I say anything, I'm going to list the main results, and then you know what we are going to do. So I'm going to work with finite EI categories. And yesterday, Jesper and Ellen, and they spoke about transporter categories and orbit categories, and these are finite EI categories. And we are going to consider various gross-unique topologies on these EI categories. And then we can, this is some sort of geometry, and then we can study shifts on site. So if a small category is given a gross-unique topology, and we're going to call it a site. And the main result is kind of straightforward calculation that we consider the shifts. So what we're going to do is we consider finite EI category and consider the so-called dense topology. And we're going to look at the shifts of sets on this given site. And we compute the shift category, which is a gross-unique topos. And it's a direct product of some G sets, and the groups are certain automorphism groups from the EI category. So the prototype is probably transporter categories and like orbit categories. And these are shifts of sets, and we are interested in linear representations. So based on this equivalence, we can continue to look at shifts of R modules. And in this case, we're going to have equivalence between the shift category of R modules and the product of some module categories of group algebras. And if we further assume R, the ring, the coefficient ring is Noetherian, then we can look at the coherent objects on the left-hand side. Then we realize the coherent objects are identified with finitely generated group modules. So this is what I'm going to do. Right. So I'm going to review some basic stuffs, and actually it's probably a little bit boring for the experts, but nonetheless, I'm going to give all necessary definitions. So C will be a small category, and actually it will almost always be finite. So I'm going to define finite category, and I ask a category to be finite if the morphisms form a finite set. And I'm going to consider EI condition. So this is, I think, first introduced by Tom Dick. And if in a category C, every endomorphism is an isomorphism, then we call it an EI category. And these are necessary to establish our equivalence. So the basic thing is that if we have an EI category, and if we have 2 objects, X and Y, and if we have 2 morphisms in opposite directions, then these 2 morphisms compose 2 isomorphisms. And that means these 2 objects are isomorphic in this category. And in some sense, we can consider an EI category as an amalgam of several groups, several automorphism groups. And because of the EI condition, there's a pre-order on the objects. So we can just set y less than equal to x if there's a morphism from y to x. And if moreover we ask C to be finite EI, then we can talk about minimal objects. So this is the basic properties that we need from finite EI categories. And so yesterday we already saw some examples. So I just visualized the examples, and this is a symmetric group on 4 letters, and I can see the non-trivial 2 subgroups. I put a circle here. It's slightly different from the the symbol Jesper used yesterday, but I put a circle here means I remove the trivial subgroup, and this is part of the poset. So DA is a dihedral group, V is declining 4, and C4 is the cyclic group, and C2 also a cyclic group, and the symmetric group acts on the poset by conjugation. This poset doesn't carry enough information of the group and necessary information, so we built some categories of it. And the next one is the so-called transporter categories that we saw already from yesterday. And it is actually a Grothendieck construction because the symmetric group acts on the G poset, acts on the poset, so we can produce Grothendieck construction. And it is a new category, and as you can see, the objects are the same as the poset in the previous page, but the group action kind of introduces many more morphisms. For instance, the 2 like cyclic group, like on the left, lower left corner, they are not isomorphic in the poset, but here they're isomorphic. And the numbers simply tell you how many morphisms there are between any 2 objects. And so there are many transporter categories because there are many given groups. We can study many G posets. For instance, I write SG for the poset of all subgroups of G, and this SPG with a circle means the poset of all non-trivial P subgroups of G. Then you can do the same thing, do the Grothendieck construction of semi-direct product to get the transporter categories. And from here, you can continue to study their quotient categories. So you identify some morphisms, and then you can get the sort of 4 orbit category and the P orbit category. Now, the abelian groups, abelian preshifts on the orbit category are quite important, as everyone knows. And so there are lots of studies into abelian preshifts on the orbit category. And all these abelian preshifts, well, I mean, a preshift is another name for contravariant functors. So all of them are from the abelian category. And so motivated by a result of ARTIM, we want to further investigate shifts on this orbit category, and other interesting categories are built from a group. And actually, I should mention that somehow this work is motivated by Palmer's work, Palmer's paper on stacks of group representations. And we try to understand how shifts and stacks can be used in group representation. And somehow we ran across this theorem, and then all of us all of our results somehow developed over this result. So I'm going to record it. So I'm going to, given a small category C, I'm going to use this particular symbol to denote, I'm not very good with, this computer stuff. Anyway, we use this particular symbol to denote the category of free shifts. And one of the important free shifts is the fixed point free shift. So if you take a G set M and you ask, you build a function of free shift that takes value on this particular G set as the fixed point by the stabilizer. Now we want to look at shifts. So in order to do so, we have to consider the so-called Grossman topologies on the category. So take the orbit category OG. If you look at the so-called atomic topology, then you get a site. So we write this in a pair, and then you can introduce the shifts on this site.
Could you just tell how the atomic topology is defined?
Yeah, you're going to see it later.
Okay,
quickly. Basically, it takes all non-empty sieves. I'm going to show you later.
Okay.
And then Artin's theorem is that you have a category equivalence. The shifts on this particular site is equivalent to the category of G set. And the proof is as follows. You take a shift on the left-hand side, then you take the value at this particular G orbit. It is obviously a G set. And conversely, if you take a G set, then you can build the fixed point pre-shift, and then you have the proof that the pre-shift, the fixed point pre-shift, is actually a shift. Then you will see, well, these two constructions or two functors are mutually inverse to each other. So, well, the original form of Artin is he considered not OG, not the site, it's the category of G sets with canonical topology. But then you use the Gilroth theorem or the comparison lemma for shift theory. You can replace the site on G set by this particular site on the orbit category. And you can find this in detail in the book of by MacLean and Moedic, Shifts in Geometry and Logic. Anyway, if you want to continue to look at representations, by the way, the Artin theory actually works for profinite groups, and actually is quite important for entire cohomology theory and for Galois cohomology theory. But anyway, we're going to just focus on finite groups. If you want to look at profinite groups, then you have to look at not all orbits. The subgroup H has to be open subgroup. But here we only consider finite and discrete groups, so we don't have to worry about topology on this profinite group. Now, based on Artin's equivalence, if you take the so-called abelian objects, then you get an equivalence between the abelian shift category and the ZG modules. But if G is profinite, then you have to be a bit careful about the module category on the right side, because in that case, you have to consider the so-called discrete G modules. But if G is finite, then you don't have to worry about that.
Where does the finiteness come in? What's the role of the finiteness?
Oh, every subgroup is open. I mean, there's no topology. Yeah. So every module is discrete.
But there's not a result like this also, like for arbitrary groups.
Well, I think as long as it's discrete, then you don't have to worry about that. But I don't know if we can go. There's some discussion in Johnston's book, but I don't know if we can go to any topology group. I have to check that.
Yeah, no, I was mainly thinking discrete groups. Yeah.
Okay, so yeah, so we are interested in orbit categories, but if you want to do more and you want to look at smaller orbit category, particularly you want to look at the p-orbit categories. And in fact, if you replace OG by the p-orbit category and you take the same kind of atomic topology, then you realize you still have an equivalence. The proof is the same. But this, for us, is not enough. We want to remove the trivial subgroup. But then there's trouble, and so we have to do something more. So before I do that, I have to recall. So you see, I recall lots of definitions. I hope you're fine with it. So I will go quickly with the definition of group Grothendieck topologies. So basically, in order to introduce sheaf, you have to have some sort of, like coverings. And in Grothendieck topology, in topology theory, you use sieve to kind of to replace or to generate the concept of covering. So basically, if you have a category C and you take an object X, and then you have a representable functor, and this is sieve. And actually, all the subfunctors of this representable functor is called a sieve on X. So there's a maximum one, which is the HX, and there's a minimal sieve, which is empty. And one can describe a sieve by a certain set of morphisms ending at X, satisfy a very simple condition. Now, you probably can consider keep this in your mind that if you have a topological space X, then you can build a poset of all open subsets, and this will be the category C. So every object in this category is an open subset of the space, and then the sieves will be some sort of covering for that open subset. Now, to define a Grothendieck topology on C, you have to meet like 3 actions. So the first thing is that the maximum sieve must be in this particular family, JC, and the second and 3. It's kind of complicated. It's not easy to explain, but the second is called stability action, and the third is called transitivity action. Basically, it mimics what you need for covering. Like the second basically says that if you have space, for instance, it's not exactly precise. If you have a space and you have a covering, and if you take a subset, then the covering of the whole space intersects with this particular subset, gives a covering of the subset. So that means it's kind of stable. And the third means that if you say if you have a space X and if you have a covering, open covering, and each member of this open covering has its own open covering, then they put all together become a new covering. So that's what these actions say. And the first one simply says an open set covers itself. So anyway, you will see some examples. So on this category C, when you introduce a Grothendieck topology, I'm going to call the pair a site, and every sieve in this topology will be called a covering sieve. And I have to warn you that it's slightly different from what you might have seen from other places. In many books with geometric background, they will have more restrictions on the category C. Particularly, they have to have the pullbacks of fiber products. And in that case, they introduce something grossly called pre-topology, or you can think this as a topological basis for the grossly topology. But for us, for finite category, usually we don't have pullbacks. Like the orbit category usually doesn't have pullbacks, so we cannot use that definition. Now, here are some examples. So on any small category, you can have the minimal topology. I mean, it has different names in the literature, but I mean, I use this one because it's meaningful. And in this case, you only choose one covering sieve for each object, the maximum one. So this is the minimal topology. But of course, you have to verify that the actions are satisfied. And the second is the maximal topology. Then you take everything, including the empty sieve. And then you can see it's also a grossly topology. I call it maximal. But these two are not very interesting. So we have to examine something in between. And here comes the dense topology. Well, the definition is concise, it's simple. I read from like McLemoy's book that they say it comes from logic, from like Paul Cohen's forcing technique, which I have no idea. But anyway, it takes a little bit time to verify that you do have a grossly topology in this by this definition. Now, if the category C meets an actual condition, the so-called OR condition, is something weaker than the existence of fiber product. So that means if you have two morphisms ending at X, then you always can complete it to a commutative square in the category C. So for instance, if you think about the categories, the orbit category of all subgroups, then you can always find a W like that. And in this case, then you see the dense topology will reduce to something that is called the atomic topology. And in this case, you take all non-empty sieves. Actually, all non-empty sieves form a grossly topology if and only if the left OR condition is satisfied. So these are grossly topologies. And now we want to consider shifts. So grossly topology are some kind of brewing condition on the pre-shifts. And now I'm going to give the probably most concise definition of the sheaf. So basically, if you look at, and if you take a pre-sheaf on C, and you take a sieve on an object X, then because by definition, S is always a it is a subfunctor of the representable functor. So the inclusion induces a natural map between the set of natural transformations. Now, if all the natural maps are one-to-one, a one-one or isomorphism, then we call such a pre-sheaf a sheaf or a J-sheaf on the side C. So you can see that the grossly topology or the sieves pose some conditions on the pre-sheafs. Only those pre-sheafs which satisfy this particular condition will be considered or will be taken out as our starting object. So for instance, there's always a constant pre-sheaf. which sends every object of C to a fixed one-point set. So I write this as F dot. And this preshift is actually always a sheaf. It is a terminal object in the preshift category. And so if you look at the definition of sheaf, then you realize both sets of the natural transformations consist of only one object. So you have a 1-1 correspondence or isomorphism of these two things. So the sheaf category is not empty. Now, if we take all sheaves and then we can form a 4 subcategory, and this is called the category of sheaves on C. And any category that is equivalent to something like that is called the grossing topos. But this is just the terminology that we do not need later on. So now we have some examples. And if we go back to the classical sheaf theory, if you take a topological space and you take the category C to be the pole set of all open subsets, then the sheaves are supplied by the so-called, the real open coverings. And then you recover the classical sheaf theory. Now, for arbitrary category, we have the minimal topology. And if we consider that, then there's no restrictions at all, because the only covering sheaf is the representable functor. So the defining map is always 1-1. And the other example is that if you consider the maximum sheaf, every sheaf is taken as a covering sheaf, then you realize that the sheaf category shrinks to just to the trivial one. There's only one object and one morphism. Now, if the category is a group, consider there's a category with one object, then you realize that there are only 2 topologies. So the minimal topology is the same as the dense topology. And under the circumstance, you realize that you either get the category of G set or you get this trivial category. Now, we go back to Artin's equivalence. So we want to figure out if there are analogous equivalents for small orbit categories, as we said earlier. So a prominent orbit category, of course, is the orbit category of non-trivial P subgroups. Now, if we look at the proofs of Artin, then you realize it doesn't work for this particular orbit category. And as you can see that, well, first of all, without this particular orbit, we cannot introduce atomic topology. But this is okay because we can replace it by the dense topology. But more importantly, when you remove this particular orbit, you actually remove its automorphism group as well. So this is somehow the reason why you can identify the sheaf category with the category of G set. But now it's gone. So we have to find another way to deal with it. So, okay, as I said, for the first problem, we use a more general topology, which is the dense topology. And for the second, we realize there's not much that we can do. So we tried sheafification. So that means we do this directly. And then we realize it works. And actually, it's not as difficult as we thought. And then we realized then after that, we can have a different proof. So we're going to have 2 proofs of our equivalence. And moreover, at first, we only look at this particular orbit category of non-trivial P subgroups, but then we realized the method works for all finite EI categories, including, groups, host sets, transporter categories, and fusion systems. But of course, I still do not understand what they mean. Let's now recall the definition of sheafification. So basically, whenever you have a free sheaf, you can do the sheafification, sheafifies to a sheaf. And the definition is given by some limit. So usually you do this in 2 steps. Given a site and the pre-sheaf, then we first construct another pre-sheaf. We call this F dagger, and it is defined on objects as various direct limits. Here, remember that when you take an object X and then this Jx consists of all, how should I say, the subfunctors of the representable functors. So they form a poset by natural inclusion. So this is the reason why you can have such a limit. And homomorphisms, it is given by the universal property of direct limit. So I did not write it up, but anyway. So by the universal property, you have a natural transformation beta from F to this F dagger between 2 pre-sheaves. And it is well known that beta is an isomorphism if and only if F is a sheaf. And moreover, for any pre-sheaf, you do this twice at most, then you're going to get a sheaf. So this is what we're going to do next. Actually, the sheafification from the functor, from the category of pre-sheaves on C to the category of sheaves on the site C, and it is the left adjoint of the forgetful functor, and actually it is exact sheafification functor. So next, we're going to compute, and it turns out that the limit, as everyone knows that in general, direct limit is not so easy to compute, but in this case, we realize that there's always a minimal sieve in this poset. So that simplifies everything. So the next step is to write down this minimal object. So one have to be careful. There's always an empty sieve, but for dense topology, empty sieve is not a covering sieve. So we have to find a non-empty one. And this is based on the definition of the dense topology, the EI condition, and also the finiteness condition of the EI category. So we can write this down explicitly. So the key lemma says that given a finite EI category, and we consider the dense topology, then on each object, we can find a unique, a minimal non-empty sieve. And so this is done as follows. So we write this down as a subfunctor of the representable functor. So you can see the definition is straightforward. Whenever you fix an object X, then you can have a full subcategory of C. We write it here as C less than or equal to X, which means you take all objects that under or below X, or you can say all objects that admits a morphism 2x. Then get a 4 subcategory. This 4 subcategory is again a finite EI category. So you have minimal objects. So if Y happens to be such a minimal object, then you take so the value of the functor on this minimum object will be the set of all morphisms in C from Y to X. Otherwise, you just take the empty set if Y is not minimal. So then, of course, you need some verification that this is really a subfunctor, and moreover, I mean, it is a covering sieve in the dense topology. Well, when X itself is minimal, then we realize that in this case, the minimal sieve is the same as the maximal sieve. This is useful in the next step when we compute the sheavification. So yeah, now with this unique non-empty minimal covering sieve, then we can compute the limit. So yeah, so we have the definition that we copied from the previous page, and when you compute it, then you know well, since you have a unique minimal object, so the limit is simply the natural equivalent, the set of natural transformation from this minimal covering sieve to F, because both of them are considered as functors on C, so it makes sense. And then you can compute this explicitly. You can do this explicitly, and actually, you will find that it is some kind of product of various fixed point sets, actually. But anyway, when you continue to analyze this, then you realize when X is minimal, F dagger X is same as Fx. And if you repeat the computation, you know, because you have to get F sharp, so you have to do this twice, and then you realize F sharp is the same as F dagger. So that means F dagger is already a sheaf. So in this way, we kind of characterize the sheaves on the finite EI categories, the dense topology. So basically, it doesn't have much to do like the how should I say this, like the structure. Well, I mean, no, I shouldn't say that. I mean, it is determined by the value of the pre-sheaf. I mean, the sheafification of the pre-sheaf is determined by the value of the pre-sheaf on the minimum objects. And you have formula to tell you what are the other values. So if we, yeah, we get the equivalence that we promised earlier. And yeah, and it actually includes Artin's theorem, because if C is the full orbit category, it has only one minimum object. And then when you put into this equivalence, and on the right-hand side, you don't have direct product, you only have one component, which is exactly the category of G set. So yeah, now it's 4, and yeah. So after this, we realized that actually the key lemma offers a different proof. So I'm going to say a few words on it. So basically, you can think it this way. So so the prototype is like you have the category of G set, and you can see the category, I mean the orbit category. The orbit category is a 4 subcategory of the category of G set. Whenever you put a topology on the category of G set, it induces a topology on the 4 subcategory. And the definition is as like is in the screen. And when the subcategory meets some nice conditions, then you can actually have some reduction. And here, I have to use another kind, a little bit awkward, but I mean, it's dense, but it's not dense as the dense we saw before. So basically, if you have a site, then you have induced subsite. And if every object in this big category admits a covering sieve and satisfying condition that every morphism from the covering sieve has its domain in the category D, in the subcategory D, then we say the subsite is dense in the original, the big site. And this is basically classical like result in topos theory that says that well, if D is a dense subsite of C, then you have an equivalence. So it's kind of reduction, and the equivalence is given by the restriction and the right kind extension. But of course, there's something that you have to do. You have to say the restriction and right kind extension actually are topos morphisms. They are not they're the usual functor, but they have to meet some conditions. So if you apply this to our case, you take C to be the category of G sets, and then you take D to the category of, to the 4 subcategory, the orbit category, then you have the equivalence. But I have to warn you that the definition of the dense subsite depends on the topology. If you take the maximal topology, you will see the induced topology or the induced subsite is always dense. If you take the minimal one, well, usually it's not. And if you take, well, the dense topology we mentioned earlier, then you get a dense subsite. And if you say look at the paper by Balmer, he has a topology called SIP, SIPP. He has a topology, and that topology also induces a dense subsite. So that means whenever you have a dense subsite, you can kind of change from the bigger category, the category of G sets, to the smaller one or to the final one, the orbit category. And this, for us, of course, it's nice because we're going to work with a finite category and finite representation. Yeah, so, well, so far, I only speak about sheaves of sets, but we are interested in linear representations. So we have to do a little bit more. There are more like concepts that I have to introduce, but these are kind of standard. These are standard. For instance, in Artin's theorem, he has the equivalence of like the category of sheaves on OG is equivalent to the category of G sets. Then he continued to take abelian objects on both sides of the equivalence, and he gets an equivalence between the representation, I mean the module category and the shift category. And this is pretty much what we do in this more general case. So in fact, as you can see from the definition that, well, if we can see the shift of R modules, what it is first a pre-shift of R modules. I mean, it's a contravariant functors from C to the category of R modules. And a pre-shift of R modules is a shift if and only if it is a shift of sets. Yeah, because every R module is a set, first of all. And then you realize the equivalence we had earlier reduced to this one. So basically, you can find the techniques from SGA4. So you fix a ring R, you take the so-called R module objects from the two sides of equivalence, then get a new equivalence. And yeah, so you have an equivalence between the shifts of R modules and the product of module category over various group algebras. And moreover, this equivalence, because now we are in, we're working with linear representation, so we can verify that this equivalence is compatible with a tensor product on both sides. So I put this is actually a tensor category equivalence. Yeah, yeah, and also, yeah, I probably should skip the remarks below that tells you a different way to get the shift category via localization or quotient category. But anyway, these are kind of standard. So in the end, I'm going to say a little bit more about finite generated modules. So here in shift category, we have to consider coherent shifts. But I mean, I probably don't have time to to go over the definitions. But anyway, in order to do so, you have to introduce like a structure shift and ring side, things like that. And then you can see the modules over the structure shift. And if the structure shift is the constant shift given by R, which means that you take the coefficient ring, then you build the constant pre-shift, and then you shiftify it, then you get the structure shift, and this is called the constant shift. And then in this case, the module category of the structure shift is exactly the same as the R module. I mean, the category of shifts of R modules on the side C. And yeah, now with this in hand, we can continue to look at the coherent objects, because the shift category of R modules is an abelian category, so we can consider coherent objects in it. And then in this case, you still get an equivalence. I mean, this is also a tensor category equivalence. And in this case, if R is Noetherian, then we actually can identify whatever on the right-hand side with the category of finite generated group modules. Yeah, this is what I wanted to tell you, and here are some like references like that probably you need to understand definitions, the constructions, and topic theory. And yeah, thank you. Nice music.
Thank you for nice talk. Are there questions? Does this work now?
Yep.
Okay. No, I just wanted to make one comment on something Fei said at the beginning, that the name of EI categories is due to Wolfgang Loeck, and I think the concept also, when he was struggling to find the right context for doing some of the computations he wanted to do as general as possible. And there was, a story about the name, I think deserves to be better. That he'd been working to find the right conditions.
We almost can't hear you.
Sorry?
You're falling out. Can you repeat what you said?
Yeah,
Sorry?
Okay, about the name, or his choice of the name, that he had been sort of struggling, trying to figure out the right definition to use, and then when he figured it out, it was so simple. All dimorphisms or isomorphisms. It reminded him of the story of, and since EI is the German word for egg, that's what he chose.
Yeah. Thank you, Bob.
Okay. I mean, I was surprised once because I was talking to Stefan Schwede, who said he didn't like the name because it sounded so funny in German, that he had no idea at that time until I told him where the name came from, if that was intentional.
Other questions?
Could you go back to your the main result actually for a second?
Yeah.
Yeah. So in some sense, this is, you're losing the structure of the category, right? Because it sort of breaks up in the automorphism. Is that intentional? I mean,
no, I mean it's kind of surprising. We thought more groups within the EI category would be involved, but yeah, it's kind of surprising. But somehow it's kind of reasonable. I mean, like if take an orbit category, and somehow, I mean, I don't know how to explain. It's like geometrically it makes some sense. Whatever, like down below will determine, the whole thing. I don't know. Yeah, I don't know how to explain this in a proper way, but it's purely by direct computation.
right. But I guess this depends on your choice of Grothendieck
Choice of the topology.
Right. So
Yeah, it heavily depends on the topology. Yes.
with another topology, you could get a richer structure. So,
Yeah, good question. Yeah, this is what we want to think about. Like for instance, if we can see the Balmer's C topology, we probably can simplify his calculation. Probably we are trying to do that, and I don't know. I mean, what kind of topology we can expect actually, apart from those I just mentioned. We have to kind of to look for interesting topologies.
Joachim?
Hi, that's very nice, Fei.
Thank you.
I just a small remark about this fact that you do the plus construction once, and that's enough to get sheaves. So usually when you have to do it twice, that number 2 is actually 0 plus 2. 0 because
Mm.
there's 0 enriched categories, usually just categories enriched in sets. If you go to higher category theory, you actually have to repeat it n+2 times. So that if you are in categories enriched over n categories, you need n+2 applications of this trick before you get to sheaves. So therefore, if we go backwards and we go down to -1 categories, you would expect you to do it only once, and that would be full sets. So I think it's surprising that, well, maybe I'm just overlooking something, but it looks surprising that you get it already once, even if EI categories are not full sets. So it's like they think full sets somehow. It would be expected that you only do it once, but now for some reason it happens for EI categories. So that looks funny. I don't know what to make of it.
Yeah, yeah, thank you. Yeah, we are still looking for applications. It's kind of surprising. We didn't expect at all that it would be so straightforward.
It's very nice. Thanks.
Any other questions?
Yeah, I have a question.
Hi, Radha.
Hi, Fei. So my question, I mean, it's just very random about the corollary. You know, you have this decomposition in terms of the automorphism groups of the minimal objects.
Yeah.
Is like at the representation theoretic level, there are also shadows of this phenomenon, right? I mean, if you take the EI category, I'm not sure I know what I'm talking about, but you take the category algebra, or you look at the, you know, the category of modules, then you get that same decomposition.
Yeah, I call this block decomposition.
Yeah, I think, yeah. So yeah, here, what you've highlighted now. So, I mean, yeah, if you don't go into the sheaves, but just look at them at the module categories, then that decomposition is, was it already known, or I don't know why my feeling is that something like that already sort of.
No, I mean, well, yeah. So there's I should say, you really have to consider the topology on C. There are various topology on the category C on a given EI category. If you take the minimal one, you just get all pre-sheaves are sheaves. So for instance, you have these atomic functors, and these are sheaves under the minimal topology, but they are not sheaves under, say, the dense topology or the maximum topology. So it's like it's like the topology it's kind of constraints that picks out certain functors from the pre-sheaf category, and this and then we can get this equivalence if you remove the condition, you know, remove the dense topology, then we don't have such equivalence.
Okay, thank you. Thank you.
Other questions? Comments? If not, we thank Fei Xu again.
Thank you very much.